So let's begin. Let's begin with lecture 11, Calc 3. So we were doing double integrals, and let me quickly recall. Recall that your double integral of a function, so you have a region D, which is a region in 2 dimensions, what I call a pancake, and you are integrating a function on this pancake. So there are 2 ways of writing this depending on the nature of D. So either you can write this as integral. So here the region is type 1. So you integrate with respect to y first, then x. So the region looks like that, where the lower bounding curve is y equal to phi1x, upper bounding curve is y equal to phi2x, and x goes from 1 to b. So this is type 1 D. And then you write this double integral as repeated integral, and this is also equal to, if the region is of type 2, where you are going to get curves which is, so now you view this way. So the top curve is x equal to psi 2y, bottom curve is x equal to psi 1y, and y varies between c and d. So you can write this as integral from c to d. This integral will be with respect to x first and then with respect to y, from psi 1y to psi 2y. And now let's try to evaluate some integrals. So we did this in the class, so we'll start with a problem which where the area was, so let me do this, find double integral. The problem was xy minus y cube, I think, dA, where d is as shown. So d was this region. This is 1 1 1 0, and that's 1 1 minus 1 0. So if we view this, so this region can be viewed both ways, type 1 and type 2. But if you, and I did it in the class by viewing it as type 2, we shall think of D in both ways. As type 1 as well as type 2 region. So we did, so viewing D, so type 1 is more convenient because then you have only one function describing the upper bound, and the lower function is also, there is only one function which describes the lower bound. When you view it, when you want to think of this as type 1, your upper curve is going to be y equal to 1, but the lower curve will be different depending on whether x is between minus 1 and 0 and between 0 and 1. So we'll have to split this integral in 2 ways. So we did this problem using viewing it as type 2, viewing D as type 2. So then there we saw that the double integral over this D of the function xy minus y cube dA, if I write this down as an integral with respect to x first, then my lower curve is x equal to minus 1, the upper curve is x equal to y, and then you integrate varying y between 0 and 1. And this turned out to be minus 23 by 40, I guess. Now we shall view it as type 1. as type 1 region. Then we'll have to do this in 2 steps. I mean, the integral will be split in 2 steps. First, you will have to integrate on this because the bottom curve here is y equal to 0. So integral from 0 to the upper curve is 1, and you have xy minus y cubed dy dx, and your x will go from minus 1 to 0, plus now your x will go from y to 1, xy minus y cubed dy, and then dx, x will go from 0 to 1. Let's calculate this quickly and see that it turns out to be 23 by 40. So let's do this. Minus 1 to 0, integral of this with respect to y first. So you will get xy square by 2 minus y to the 4 by 4, and that is between 0 to 1 dx, plus integral 0 to 1. Again, you are going to get xy square by 2 minus y to the 4 by 4 between y to 1 dx. So this is going to be, if you integrate this with respect to, now I have to evaluate this first. At y equal to 1, I get x by 2 minus 1 by 4. At y equal to 0, I get 0, plus integral 0 to 1. At y equal to 1, I get again x by 2 minus 1 by 4, minus at y I get, sorry, this should be x, isn't it? Because you are integrating, the lower curve is y equal to x. So I get x cubed by 2 minus x to the 4 by 4 dx. Okay. All right. So then you integrate this. So you are going to get integral of x is x squared by 2. So you'll get x squared by 4 minus x by 4 from minus 1 to 0, plus x squared by 4 minus x by 4 from 0 to 1, minus integral of x cubed is x to the 4 by 8 minus x to the 5 by 20 from 0 to 1. And that's going to be 0 minus 1 by 4 minus minus 1 by 4 plus (1 by 4 minus 1 by 4) minus what do we get here? 1 by 8 minus 1 by 20. So this will vanish, this becomes half, so you get minus half minus 1/8 minus 1 over 20. So if you find the common denominator, which is 40, you get minus 20 minus 5. The last sign is plus 2, so that's minus 23 by 40. Good. Let's do another one. So compute double integral of 4 minus y square dA over d, where d is the region bounded between y square equal to 2x and y square equal to 8 minus 2x. So you see that these both are parabolas. So these are parabolas opening sideways. So you should be able to draw the pictures of this, which is, so the first step is always draw the sketch. First step, sketch D. Sketch the region D. So y square equal to 2x is this parabola. And then y square equal to minus x will be something like same thing, except it goes the other way around. But this is not minus x, but it's minus 8 2x. So you can write this as minus x minus 2 comes out, minus 2 times x minus 4. So the vertex of that parabola is 4, because when x is 4, y is 0, and it will open the other way around. So this is y square equal to 2x, and this is y square equal to minus 2 times x minus 4. And so these points of intersection with y-axis, which is what we will need, these are when x is 0, so y square will be 8. So these are 2 root 2 plus minus. So this is the region we are talking about. Required D. So now you see that if you view this as type 1, then we'll have to divide it into two pieces, because the bottom curve and the top curve both change at this point. Whatever that point is, we can find the points of intersection. That is what we will need. But if you write it as type 2, then it's much easier. So observe that it is advantageous to view D as type 2 region, where the top curve then will be just one curve and the bottom curve will be another curve. We will need these points though, the points of intersection. So that we will find first. So first we shall find, because that's what we'll need when you look at the limits of integration for y. So we shall find the points of intersection of these curves. So we have to solve the equation y square equal to 2x and y square equal to 8 minus 2x. So if I just add them, what do I get? Isn't that what we have? Yeah, y square equal to 2x, y square is equal to 8 minus 2x. So if I add them, I get 2y square is equal to 8. So y is equal to, y square is 4, so y is plus minus 2. So this point is 0 minus 2 and this point is 0, 2. So now we will write this integral, double integral over D of the function 4 minus y square dA equal to, I will integrate with respect to x first, because you are viewing this as type 2, and then with respect to y. So my y is held fixed, x goes from there to there. So the lower curve is, so now you have to write these curves. The first curve y equal to 2x will be written as x equal to y square by 2. And your second curve is, so this is your first curve, this is the second curve. This you will write as x equal to 8 minus y square by 2, which is 4 minus y square by 2. Good. So this will be going from, so what is the lower curve? The lower curve is y square by 2. The upper curve is 4 minus y square by 2. And y will run between minus 2 to 2. So let's evaluate this. So this is going to be integral minus 2 to 2. Integral of this is going to be 4y minus y cubed by 3 between y square by 2 to y 4 minus y square by, sorry, I made a mistake. I'm integrating with respect to x, so you cannot make this mistake. So the integral is much easier, 4 minus y square times x, and x will run between y square by 2 to 4 minus y square by 2 dy. So this is minus 2 to 2, 4 minus y square times x. X is 4 minus y square by 2 minus y square by 2 dy. So that's going to be minus 2 to 2, 4 minus y square. Into parenthesis, I get 4 minus, this is going to give you just 4, isn't it? Minus y square by 2. Not, so they will add, so you'll get 4 minus y square. Good. So this is just going to be integral minus 2 to 2, 4 minus y square square, which is 16 minus twice the product in the middle plus the square of the last term. So this is going to be 16y minus 8y cubed by 3 plus y to the 5 by 5 between minus 2 and 2. So this is 32 minus 8 by 3 times y cube is 8 plus 32 by 5 minus 16 minus y cube by 3, which is minus 2 to the 3 by 3, 8 times, and plus minus 2 to the 5 by 5. These are going to add, right, isn't it? This is plus and this will be again minus plus, this is minus and minus, so this is just going to be twice 32 minus 64 by 3 plus 64 by 32 by 5. So it's going to be whatever it turns out to be. You multiply by 15 times 32 minus 64 times 5 plus 32 times 3 will be 96, that I can calculate, over 15, and that's going to be 330, 480 I guess, and 64 times 5 is 320 plus 96 by 15 times 2. So that's 160 plus 96, 160 plus 96 is 256 by 15, which is 512. Okay, so that's that. Let's do one more. Problem number 3. So as we saw that the double integral represents the volume of the solid whose base is D, sides are just cylindrical perpendicular to the xy plane. So let's do the following problem. Find the volume. So you can be asked to find double integrals by asking you to find the volume. So find the volume of the solid bounded above by the surface z equal to y square and below by the xy plane. And now you have to be told about the sides, and on the sides by z1 minus by x equal to 1 minus y minus 1 square and y equal to x. So let's try to draw the picture first. So I'll draw the vertical view with x and y axis as if you are viewing from z axis. So this, you see, y equal to x is a straight line, and then x equal to 1 minus y minus 1 square is a parabola. So if you look at x equal to minus of y minus x equal to minus y square, you know, opens on the side. This is x equal to minus y square. But this is not minus y square, it's y minus 1 square. So that will be shifting everything vertically. So let me erase this. And so this parabola will be with vertex at 1, 1. This will be x equal to minus of y minus 1 square, because when y is 1, x is 0. And then this additional 1 here will push it in the x direction by 1 unit. So it's a parabola whose vertex is at 1, 1. So I have this one, and this parabola will also cut when x and y, when x is 1, when y is 1, x is 1, and when y is 0, x is 0. So it will cut through this. That one doesn't look like a parabola, but alright, so let me draw the picture again. This is the line y equal to x, and this is the point 1, 1, and the parabola will be having a vertex here. And when will it cut the y-axis? That's when x is 0, y minus 1 square equal to 1. So it will cut y-axis at 0 and 2. So you are looking at this region. This is the region D over which you have to integrate. And now the surface above, you don't have to draw this picture, but you have this curve y equal to z square, which is a parabola in zy plane, something like this. And this has no x in it, so the surface is just the vessel, which is like this. So this kind of a surface is on the top, and you are looking at some piece here like that on the bottom. So I can't draw this surface, but you see the picture. The top surface is going to be the, if you look at this kind of parabolic tray, then its lower surface is going to be the upper bounding surface of the solid, whose base is, so base is D. All we need is base. Good. So how do you find the volume of this solid? Let's do this. So this is going to be just the double integral of the surface f of xy dA. So this is the formula for the volume, and your curve on the top is z equal to y square, right? So f of xy is y square. So this is your z. So this is going to be y square dA. And now this region D can be viewed as type 1. So view D as type 1 region. You can also view this as type 2, doesn't matter. But let me view this as type 1 and we'll see what we get. So this is going to be y square dy then dx, and y will go freeze x, so y will go from the lower curve to the upper curve. The lower curve is y equal to, so you have to write this in terms of y equal to, if that's going to take, that will need us taking the square root, so maybe it is better to view this as type 2. Let me write down viewed as type 2. What do we get? That may be easier to write because your curves are given in the form x equal to a function of y. So if you view it this way, then the lower curve is x equal to y and the upper curve is 1 minus y minus 1 square, and this will be y squared dx, and then with respect to dy, and the lower curve, and your limits will go between 0 to 1. If you write it as type 2, the only trouble is your lower curve will be y equal to x. Lower curve will be equal to, so you have to rewrite this equation, x equal to 1 minus y minus 1 square. So I will write this by flipping the x's and y on either side. So you get y minus 1 square equal to 1 minus x. So y minus 1 is going to be root 1 minus x. And then you move y to the 1 to the right hand side. So it's y equal to 1 plus root x, 1 minus x. So this will go from the lower curve, which is y equal to 1 plus root 1 minus x, to the upper curve, which is x, and then x will run between 0 and 1. So it's better not to get into the radicals, so let's compute it using so another thing, this example teaches us that many times the area can be viewed in both ways, type 1 or type 2, but the integration may be much easier if you view it one way or the other. So you choose depending on what you have. So you now get y times 1 minus y minus 1 square dx, and now have I done this right? I am integrating with respect to x first, yes, and so my next thing will be dy. So this is going to be 0 to 1 y square into bracket 1 minus y minus 1 square right. This is y to the 2, it's not y to the minus 2, this is okay, minus y square times y dy. So let's see what that turns out to be. 0 to 1 is going to be y square into parenthesis 1 minus y square minus 2y plus 1 minus y cube dy. And so that's going to give us y square into parenthesis minus y square plus 2y, 1 and minus 1 will cancel, minus y cube. That's integral 0 to 1 minus y to the 4 minus plus 2y cube minus y cube will give you y cube, right? Minus y to the 4, 2y cube minus y cube. So this is going to be minus y to the 5 by 5 plus y to the 4 by 4, 0 to 1, so it's 1 minus 1/5 plus 1/4, which is, the denominator is 20. So the volume is 1 over 20. Good. So that gives us good practice with computing double integrals. Let's move on to regions of type 3. And that is with polar coordinates. Regions of type 3 using polar coordinates. So suppose I have a region which is described by two curves r. Now I'm giving you two functions, r as a function of theta. In polar coordinates you are writing functions as, let's call this r equal to psi 1 theta, and the other upper bounding curve is r equal to psi 2 theta. This is r equal to psi 2 theta, r equal to psi 1 theta. So you're looking at, and my theta goes between theta 1 and theta 2. So this is the region we are talking about. This is your D. So D is going to be r thetas such that theta runs between theta 1 and theta 2, and r runs between psi 1 theta and psi 2 theta. So sometimes polar coordinates are useful, as we'll see in a problem, and then integrating over a region D in polar coordinates will be more advantageous than using rectangular coordinates. So this is our D. So here the only thing you have to learn is the key fact is dx dy or dy dx gets replaced by r dr d theta. So there is an extra r here, and this I will explain for a minute. So in a minute, if you take a region D and if you are using Cartesian coordinates, you remember we made this partition. This is our xi minus xi plus 1, yz plus 1, and so typical element here was a rectangle. A typical what should I call, typical piece of the partition is a rectangle with area what I call dx dy, which is actually xi plus 1 minus xi times yi plus 1 minus yz plus 1 minus yz. So that's a typical area which you are using to write down the double integral as a function's minimum of the function on this interval to form the lower sum multiplied by the area. Now if your area is going to be measured in polar coordinates, you will take a partition of r and theta. So you will take a partition of theta. So let's call this is our theta 1, theta 2, and I will also have a partition of the r's. So if I look at a typical piece here, if you look at these two, so this is going to be my theta I plus 1, or theta I and theta I plus 1. So if I look at a typical piece here, it looks like that. Here is my Ri and here is Ri plus 1. Here is Rz, I may call, maybe I'll call this Ri plus 1, and theta z plus 1. So this area, a typical area here, is going to be this side. You learn this in trigonometry. This angle is, which I will write as d theta. D theta is just theta z plus 1 minus theta z. So this is d theta times r. The area is going to be r times d theta multiplied by dr. By dr is going to be r I plus 1 minus ri. So the shape of the area is different. It's not rectangular, but the area is going to be given by r times a small change in theta variable and small change in r variable. Here the area is given by small change in x variable and small change in y variable. So it's dx dy. So when you form this sum, the lower sum and the upper sum, in this situation, in the polar coordinates, we will have an extra factor of r. So therefore, our double integral of f, which is expressed now in terms of r theta dA on a region which is of type 3, you will integrate first with respect to r, but in doing that you will have to have an extra factor of r dr d theta, and then r will go from psi 1 theta to psi 2 theta. Theta will run between theta 1 to theta 2. So that's how you do double integrals when you have a region which is described in polar coordinates more easily as a region in between two polar curves r equal to psi 1 theta, r equal to psi 2 theta, and theta 1 varies between theta 1 and theta 2. So let's do one problem based on this. So find the double integral over d of root x square plus y square. Sometimes, you know, the function is not given in terms of r theta, but by looking at the curve you see that it is better to use, its advantages to use the polar coordinates, where, so let me say, where d is the region inside the cardioid. So what is cardioid? That's right. So it's a heart-shaped region, and it's a, so you might not have studied polar curves in detail, but once in a while they come up. So this is a curve whose equation is given in polar coordinates, r is equal to r theta, which is this, and so you should learn how to plot this. It's not very difficult. You will rarely get these problems, but you should know this. So when theta is 0, so theta varies between 0 to 2 pi. Let's try to plot. First we plot d, or sketch plot d. Plot d or sketch d. Usually you use the verb plot to talk about a curve. We want a region which is bounded by this curve. So when theta is 0, r is a, and as theta increases, r will increase, and when theta is pi by 2, r will be 2a. So it's an increase like that. Now this function, you will see, as theta goes between pi by 2 to pi, at pi sine theta will be 0, so r will be again a, and the angle is pi, so you will be at this point, and it's going to be symmetric. And then when theta is, so this is the polar coordinates of these points are a 0, these are 2a pi by 2, this is minus a, or I shouldn't call, r is always positive, so it is a pi, and now as theta increases, sine theta is negative, and at 3 pi by 2 sine theta is minus 1, so this becomes 0. So you get a curve which is like this. So this is why it is called cardioid, because it looks like a heart-shaped curve. And this curve, if you want to write it in Cartesian coordinates, the equation will be absolutely messy with the inverse trig functions and so on. On the other hand, you know the conversion, because for the function is given in terms of x and y, but you know x is r cos theta, y is r sin theta. So actually the function is not too difficult to write in terms of the polar coordinates, it's just r. So therefore our integral will be, so you see that the lower curve is r equal to 0, the lower bounding curve, and upper bounding curve is r equal to a times one plus sine theta, upper bounding curve for this region. So for example, when you are integrating on such regions, it's much better to use, so this is going to be r dA, and so it will be double integral dA will be r dr d theta. First integration with respect to r, then with respect to theta. R goes from 0 to a times 1 plus sine theta. Theta will run between 0 to 2 pi. So this is going to be integral 0 to 2 pi. I forgot to have, I have an r and then another r dr d theta. So this will be r square dr d theta. R between 0 to a times 1 plus sine theta. So this is going to be integral 0 to 2 pi r cubed by 3, 0 to a times 1 plus sine theta d theta. So it's 1/3, let's take it outside, 0 to 2 pi, and the value of this is 1 plus sine a cube, 1 plus sine theta cube, and at 0 you get 0. So this is what you have to do. So now this is a little messy integral, but it's not too bad. You know how to expand. A plus b cube is a cube plus 3a square b plus 3ab square plus b cube. That's your pre-calc. So you are going to get this expansion. Now if you look at the integral of this, so let's write down the integral is not difficult. It's going to be theta between 0 to 2 pi, and I claim that the other integrals will vanish. For this you need to work a little bit. I'm not so sure about sine square. Sine square, yeah, I mean this is not difficult to see. Sine square, you know, you have to use the double angle formula for this. Cos 2 theta is 2 cos square theta minus 1, or is 1 minus 2 sine square theta by 2. So sine or theta, so I'm writing already the double angle. So sine square is 1 plus cos 2 theta by 2, 0 to 2 pi, plus sine cube theta d theta. So I claim that this will be 0, this will be 0, and cos 2 theta when you integrate, that will be 0. So we'll get 3 by 2. So I get a cube by 2, and this will give me a 2 pi. This will give me 3 by 2 times 2 pi, and the rest will be 0. So I think this is what the answer should turn out to be. So it is 5 pi by 2 times 2, so it's 5, am I right? It's 5 by 4, and then you will have a 2 pi a cube. So it's 5 by 2 a cube pi. Good. So now let's move to the next bit. So we have seen regions of 3 types, how to find the double integrals, and now we will see how to use double integrals to compute surface areas. So surface area of the surface z equal to f of xy, its projection, I will call it over the region D. What I mean by this is the following. I have a function of 2 variables defined on D, and I have a surface which is the graph of this function. This is z equal to f of xy, and I'm interested in finding the surface area of this. So I will first write down the result and then give you a proof of that, and then we also see how to compute. So surface area of sigma, and sigma is described by all points x comma y comma f of xy. So your z is f of xy, where xy varies over D. So surface area is given by double integral over d of root 1 plus fx square plus fy square dA. So this is the formula for surface area of surfaces like this. And how do you get that is another matter which we will get to. Yeah, we'll get to that in a minute. Let's do one more problem. So I think this is problem 5. So compute the surface area of the surface z equal to 9 minus x square minus y square above the plane z equal to 5. So as in double integrals, you have to first draw a sketch so you understand how the region looks like, and then you will be able to get the limits of integration. So above the plane z equal to 5. So how does this look like? So first of all, draw a sketch of this. So you see that this surface, if you freeze z, then it's going to be a circular thing, circle. So this will be, the cross sections will be circles, and when z is 9, x and y must be 0. So when z is 9, you get the point 0, 0, 9. If x and y are, if you are in the xy plane, if z is 0, then the intersection with the xy plane is a circle of radius 3. My circle doesn't look right, so let me try to draw maybe like this. So it's a circle of radius 3. That's your x square plus y square equal to 0. Hold on. This scale I have to get removed. I have to get on the side. Let's see what happens now. Okay, so this is a vessel, this is a cap, this is a vessel or a object like this with circular cross sections, and now I take z equal to 5, and so I will get this circle, and we are talking about the surface area of this solid. So the surface area we are looking at. Good. So what matters is you want to write down what is the projection of this on the xy plane. So we need to find our d. The projection on the xy plane of this surface. That's the area over which we are going to integrate. So what is this thing going to be? That's not difficult. When z is 5, what is the radius of that? When z is equal to 5, you get 5 equal to 9 minus x square minus y square. So that means x square plus y square is 4. So this is a circle of radius 2. So therefore the projection is going to be a circle of radius 2. This original circle was of radius 3. And so this is, so d is going to be the disk of radius 2. Good. So therefore surface area is going to be integral on this d. So d is going to be set of all points x, y, for which x square plus y square is equal to 4. And the function is 1, and what you are integrating is integral root 1 plus fx square plus fy square dA. So now let's look at what is fx and fy. So f of xy is z, which is 9 minus x square minus y square. So fx is going to be minus 2x, fy is minus 2y. So the surface area is going to be integral on d, and now you know the picture of d. Picture of d is just this circle of radius 2, and what we will have here is root of 1 plus 4x square plus 4y square. dA. Now you see polar coordinates are much better, because integrating this with respect to x or y is very difficult. So polar coordinates will be good to do this. So I write this as, because this x square plus y square is r square, so I will have to integrate 1 plus 4r square. dA will be r dr d theta, and r is going between 0 to 2 and theta is going between 0 to 2 pi. So this is a much easier integral to calculate. So this is going to be, now you will have to evaluate this, but this is not difficult, because, so let's evaluate integral root 1 plus r 4r square. There is a r outside, so this makes it easy. Without the r it will be a trigonometric substitution. So you put u equal to 1 plus 4r square, so du will be 8r dr. So this integral will be integral root of u d times r, and dr will be du by 8r. So this r cancels with r, and you will get 1 over 8 integral u to the half is u to the 3 by 2 over 3 by 2. So that's going to give you u to the 3 by 2 over 12. Good. And what is u? u was 1 plus 4r square to the 3 by 2 over 12. That is what we will get. So this integral will be 1 plus 4r square to the 3 halves over 12, 0 to 2 pi d theta. I have evaluated between 0 to, no, I have to evaluate it between 0 to 2. So integral 0 to 2 pi, let's pull out 1 by 12 outside. Let's pull this outside. And what do we get? When r is 2, this is going to be 1 plus 8, which is 1 plus, it's going to be 17, isn't it? Hold on one sec. Yeah. So it's going to be 17 to the 3 halves minus, at 0 this will be 1. 1 to the 3 half is 1. This thing times d theta. And so this is going to be 2 pi by 12, 17 to the 3 halves minus 1, which is pi by 6 times 17 root 17 minus 1. So that's how you calculate surface areas. Now let me give you a reason for where this formula comes from. So the proof, or rather sketch of the proof. For this formula. So what you got to do is you look at, so what was our thing? Our region is D, and I'm interested in looking at a surface area. So we remember we took a partition. This was my xi plus 1, and I took a yj plus 1. And this is the region that we were looking at, and then you are looking at the function. Let me draw a picture like this. This is a little, it's blocking my previous view, so I need to erase this and make a line. Let's make y line a little bit further out. I'll draw a bigger picture of D. So my yz's are here. This is my D. Y. So this is my, yeah. So now I'm going to draw a picture of you have to do these things very carefully, otherwise it erases wrong lines. Alright, so now I look at, this is my xi, this is my xi plus 1. So I call this point A, and I take this vector AB bar. Similarly, I will look at, suppose let me take the value of y over there to be that. So let me call this point B and this point C. And my surface over this is going to be, the area will be approximated by this parallelogram. So the area of the surface of the piece of this surface over the small rectangle xi to xi plus 1 cross yz to yz plus 1 will be approximated by, approximately equal to area of the parallelogram AB generated by vectors AB bar and AC bar. Now note that, so I'm making, let me call this H and this one K. So note that AB bar, which is going to be B bar minus A bar, is going to be the change in the B coordinates is going to be H. There is no change in the Y coordinate, and we are going to approximate. So we are using by mean value theorem, the value of the function at B minus the value of the function at A is roughly like taking the x. So you are applying this, because you are changing only x and y is kept fixed. This is going to be the value of the derivative of the function at some point in between. So I take some point in between. I will not denote it by, let me write it like this. It's the value, this times the width, which is h. So this is the function's x derivative at some point. What should I call this point? I will call it Piz. Piz is some point here. That thing doesn't really matter, because in the limit, which point you pick here, whether you take the minimum or the maximum or any point, doesn't matter. In the limit, the sums will converge to the same limit. But anyway, so this z component will be fxh, and similarly AC bar, so that's why I said this is a sketch of the proof. This is going to be, now if you look at AC bar, the vector C, AC bar is going to be C bar minus A bar. And in this case, you see the x coordinate doesn't change, y coordinate changes by k, and the corresponding height will be the partial with respect to y, comma, times k. And so if you look at this expression, so what will be AB bar cross AC bar, which is the area of the parallelogram, area of the above parallelogram, This is going to be the cross product, norm of the cross product. Remember, norm of the cross product is always the area of the curve, and so this is going to be Ijk. Let's take the norm later, or maybe I can put an absolute value, and then you are going to have h0 fxh and 0k fxk fyk. So if I compute this is going to be norm of the vector k hk fx comma minus hk fy minus here and then 0. And so this norm turns out to be root h square k square fx square plus fy square. It is not 0 because it is hk. Here it is hk. So it's going to be hk square plus hk square fy square plus h square k square. And so if you write this, you get hk times root fx square plus fy square plus 1. So when you form your sums, when you form your Riemann sums, you will have, if you are counting the patches of the surfaces, you will get the summation of such terms. You will have the surface area over the xi plus 1 cross yj plus 1 patch. If you are counting the surface area, this is going to give you exactly this thing. This is going to be your little xj minus xi or whatever. H is your xi plus 1 minus xi, yj plus 1 minus yj, multiplied by the value of this function, root of fx square plus fy square plus 1, evaluated at some point which I call Pij. But this is exactly the Riemann sum which will converge to the double integral of this function. So the theorem says that, so what I didn't tell you probably before is I just mentioned the theorem where we form the sums by taking the minimum and the maximum. But when the function is continuous, you could take any point you wish in the rectangle Rij, form the sum. That sum also converges to the integral. That fact we are using. So this sum will converge to that, but the sum on the other hand is going to be converging to the actual area because you are chopping the area into pieces, bits and pieces, and that sum is going to converge to this, which so the total area is going to be that. That's the sketch of the proof, and that is where we will end this discussion of double integrals. Let me take a little breath because we want to move ahead. Good. So now I want to introduce you to the next notion of an integral, and that is a very important concept called the line integral of a vector field. So you have learned how to integrate scalar fields over pancakes. Now the next chapter. And that is, let's give it a heading, line integrals. I told you that we are going to learn various kinds of integrals and they will have meaning in physics, as we'll see. Well, the first one which we saw about double integrals of scalar functions doesn't have much to do with physics. It gives you geometric, it measures the volume of a solid. Now what we are going to see has a meaning in physics. So this is the line integrals of vector fields. So what we have is a vector field defined on a domain in R3, and you have a curve in this domain, and we'd like to define what is meant by line integral of a vector field along a curve. So you have this region D in R3 and you have a curve inside this C. So let f bar and this is a vector field. This is from D, which is a subset of R3, to R3 be a vector field. Vector field is just a function from R3 to R3. So let this be a vector field. Then, and let C is equal to R bar T. T varies between some 2 points. T is equal A. T is going from A to B. Be a smooth regular curve inside D. So I want to define what is meant by line integral of a vector field along this curve. So we shall now see the concept of a line integral of f bar along the curve C. This has a physical interpretation. So what you are trying to do is you are computing what you call in physics. So this is your curve, let's say C, which is the image of the function R bar T. T varies between A to B. T is in the interval A to B. So this is your R bar A, this is your R bar B, and this is inside the domain D. So now I take a typical point R bar T, and what you want is the concept of work done. So the idea is the following. So think of this D as a domain on which there is an electric field, electrostatic field, which is F. So F of x, y, z is, think of this as a electrostatic field, whatever that means. That means if you have a charge on yourself, then you will get a shock or something. Then if you have a point here which is a charged particle, then because of this force it will try to move in some direction. Now what you got to do is we want to move this along a particular curve. So because of the vector field, this charge will try to run away in various directions depending on the strength and the direction of the vector field, but you want to move this charge along a particular curve. So you have to do some work. This is the concept in physics, the concept of work done by force. So if you have a force acting in physics, also you can think of this as some force, and you want to move a particle along a particular curve in a certain through some distance, then the force, work done by a force in moving a particle, I'm motivating the definition here, through distance s is, so if the force is acting in a certain direction, you are moving in a direction u bar, then it's going to be the component of the force in the direction of the vector u bar and multiplied by the distance. So this is the concept of work done. Work done by the force in moving through distance s, if the force is acting in the same direction, it is given by the product of the force times the distance it moves the point through. So if the force is acting in a different direction, what you do is take the projection. This is what basic physics tells you, that when your force is acting in a different direction, you are trying to move in a direction u bar, it's the component of f in the direction u bar that matters. The component perpendicular to that will not move this point. So you take the dot product and multiply it by the distance. That's the idea. So that's the concept of physics. So now I take this curve and I take a partition P with a partition of the interval a equal to t naught less than t1 up to tn, which is B. And now I look at this point, let's call this R at, so let's take this, my whole curve got erased, but that's fine. We can draw another curve. So I will take these values R bar t1, R bar t2, R bar ti, R bar ti plus 1, That's my r bar b somewhere here. And so if I look at this, I look at this distance. If my partition is fine, then I can approximate the distance by the straight line, by the curve by the straight line. So the work done in moving a charged particle, if you think of this as electrostatic field, in moving from r bar ti to r bar ti plus 1 is equal to the dot product of this vector field f bar with r bar I plus r bar at ti plus 1 minus r bar at ti. Now we use the fact, now here we are using mean value theorem. Difference between the values of a function at 2 points is actually approximately the derivative of the function at some point in between, which I call ci. Ci is some point between ri and ti plus 1. So ri prime at ci times the width, which is ti plus 1 minus ti, by mean value theorem. And so the total work done, so therefore, so work done by force in moving the points of my, that's what we should have. So therefore the total work done, so this is the concept in physics which this concept of integral is going to capture. So the total work done by f bar in moving a charged particle from r bar A to r bar B along the curve t goes to r bar t is equal to the sum of this function that we wrote down. So it is f at r bar t. So I'm taking the values at r bar ti multiplied by the value of the derivative, dot product with the value of the derivative at ci times the width ti plus 1 minus ti. So you see that this sum is going to converge when the partition tends to infinity. I mean the partition norm tends to 0. This will converge to the integral of f bar dot r bar prime t dt. So if my f bar is going to be, say, mi bar plus nz bar plus nk bar, and my r bar t is going to be xt comma yt comma zt, then this will converge when I indicate this by arrow as norm p tends to 0, as the partition is made finer. Finer and finer. So what you get at the end is you integrate the function m xtyt zt, so which I will not write because it will be too long. You know that m is a function of x, y, z, and so r prime is going to be x prime t, because so r bar prime, maybe I'll write it. So this is, so my r bar prime is going to be x prime t, y prime t, z prime t. So therefore f bar dot r bar prime will be just m x prime plus ny prime plus, what did I call, m, n and p, I should call p z prime. And therefore your integral, so the work done by the force will converge to, so I should say it like this. Therefore the total work done equals integral a to b mx prime plus ny prime plus pz prime dt. This quantity is called the line integral. This quantity is called the line integral of f bar along the curve C from r bar A to r bar B. And so it measures something in physics. It measures the total work done. This is the meaning of this quantity. So I want to evaluate this first, then I will try to, maybe one more thing. This quantity is denoted by, this integral is denoted by the symbol, and I'll explain why it is this symbol. Is you write f bar dot little t bar. Remember, little t bar is a unit tangent vector to the curve ds on C. This is one notation. Or another notation is you also write this as f bar of r bar t dot dr bar along C. So we will use these two notations, and this is a scalar. This quantity is a scalar and has a meaning in physics. If f bar is thought of as a force, f bar is, or a field, thought as, if f bar is thought as a force field or just a field as physics people will call it, it's the work done in the field F to move a point from r bar A to r bar B along the curve C. So let's first, for math, we will first try to compute these things, then I'll tell you why these two notations actually capture this idea. So first, some problems. So in this new chapter, I'll call this problem 1. So let's do the problem. Let's take f bar. This is given to be in two variables. So we are talking about R2. So this is x square minus y square I bar plus 2xy is a bar. And C is the straight line. C is a straight line from 1, 1 to 3, 1. Or 3 minus 1. Find integral f bar dot dr bar along C. That's where I'm using this notation. So you have to find this line integral. So let's see what's happening. So you have a curve joining 1, 1 to 3 minus 1. That's this point, isn't it? 3 minus 1. This is your curve going that way. As we will see that this integral will depend on the direction in which you traverse the curve. So first thing is to get an equation for C. So first get an equation in the parametric form. Get a parametric, and this you are done in pre-calc, parametric equation of the curve. So a very useful formula from pre-calc is equation of a line through a point. So this is the only formula that you need, through P equal to A comma B with slope M. is y minus b equal to m times x minus a. This is what you will need, a useful fact from pre-calc. Useful fact from pre-calc. So I want to compute, first of all, slope is going to be difference in y coordinates -1 over 3 minus 1, which is -2 over 2, which is -1. So therefore the equation of this line is y minus, now we pick 1 1, y minus 1 equal to m times x minus 1. So the equation is y equal to 1 plus, well, I'm doing it a bit faster than I should. So I will write this as y minus 1 equal to minus x plus 1. So I write this as y equal to minus x plus 2. That's your Cartesian equation. So in parametric equation I take, so x as the parameter. Parametric equation will be I take x equal to t, so you will get r bar t is equal to t comma minus t plus 2. Y is, so it is t comma yt or xt. In the function, if you call this function as a function of x, then it is f of t. So that's the parametric equation. Now you have to make sure that the curve is traversed in the right way as you move from, so which will give you 1 1. So if I put t equal to 1, I get 1 1. So at t equal to 1, r bar 1 is 1 1, and my r bar at to get to 3, I need t equal to 2, t equal to 3, isn't it? So this will give me 3 comma minus 1, so r bar 3. So now I have parameterized the curve. So integral f bar dot dr bar over c is going to be integral from t equal to 1 to 3. F is, what is my f? F at xy was x square minus y square comma 2xy. Right, that was my function. Yes, so now my x, I want to evaluate this at r bar t. So your xt, in other words, is going to be t, and yt is minus of t plus 2. So this is going to be f bar, which is, so let me first write it as x square minus y square comma 2xy dotted with r bar dash t dt. So let's write this as integral 1 to 3. Now my xt is t, yt is minus of t plus 2, comma 2xt, xt is t, yt is minus of t plus 2, and dotted with r bar dash. What is r bar dash? I should have calculated this somewhere, so let's do this. Maybe I'll write it better here. Yeah, good. So r bar dash is going to be 1 comma minus 1 plus 2, which is the slope 1 1. R bar dash is 1 1, it's independent of the point. Xt is going to be t, and yt is minus of t plus 2. So I'm just substituting xt yt, and I'm taking r bar dash, which is 1 comma 1 dt. So this is going to give you integral from 1 to 3. This is t square minus 1 minus t square times 1, I'm taking the dot product, plus 2xy, so it is 2t times 2 minus t times 1 dt. So then we have to just compute this. So integral 1 to 3, you get t square minus 1 minus 2t plus t square plus 2 times, let's multiply this out, so you get 4t minus 2t square dt which is going to be, so this t square minus t square cancels, and then you have minus 2t square. How many t's? We have plus 2t and plus 4t's plus 6t, and then you have a minus 1. Between 1 to 3. So that gives me minus 2t cubed by 3 plus 6t square by 2 will be 3t square minus t between 1 to 3. So this is minus 2 by 3, 27 plus 27 minus 3 minus the value at 1 is minus 2 by 3 plus 1 minus 1. So that involves just some computation. This is going to be minus 18 plus 20. So minus 18 minus 3 is minus 21. So this will give you just 6. And this will give you plus 2 by 3. So you get 20 by 3. I hope I haven't made a mistake here. I made one mistake probably, because my slope I think is not right. That's why my answer is not right. My r bar prime is minus 1. Sorry. So how will that change things? This is minus 1. That means I will subtract at the end. I just multiplied, and the second term, this will be my negative, and this will be negative. This will be positive. So these are my corrections. And so if I do that, let's do this again. Hazards of online teaching. You can always try to compute this on the spot, and then you can make an error, a simple algebraic error. So let's see, let's double check. So I made one mistake, which is putting a minus 1 there. It should have been minus 1. So I change this sign. So I get minus. This sign becomes minus, isn't it? So this sign becomes minus. So let me correct this. This is minus. And the other thing will become plus. Now everything should be okay. So now let's see how many t squares we have. 2t square plus 2t square is 4t square. Then minus 2t minus, this is 4t minus 2t is minus 2t minus 1. Is that how it is going to be? Let's see what it turns out to be. Okay, whatever it is. So 4t cubed by 3 minus 2t square by 2 minus t from 1 to 3, which is going to be 4 times 27 by 3 minus 9 minus 3 minus 4/3 minus 1 minus 1. This will give you 9, so 36 minus 12 is 24 minus 4 by 3 plus 2. Let me see this in a second. Yeah, this sounds okay. So this is 26 minus 4 by 3, which is whatever it is. 26 times 3 is 78, right? So it is 78 minus 4, 7. Yeah, 78 minus 4, 74 by 3. Now it's more or less done, but let me do one more problem and then we will stop. So problem 2. Let's do find the line integral f bar dot dr bar over the curve C, where you are given a vector field f bar of x, y, z to be minus zi bar plus xk bar, and C is the semicircle from 101 to minus 100. So first you have to draw the picture of this semicircle. Let's draw the picture in the xz plane. This is in the xz plane, isn't it? 1, 1, 0, 1. Y component is 0. Let's make this 0, 1, 0. That's much better. So I have this point 1, 0, 0, and you go to minus 1. X is minus 1, z is 1, z is 0. So x is minus 1. So this is the semicircle we are talking about. If you draw the, usually I draw the picture which is in 3D, I draw the x-axis like this. So this is lying in the xz plane. So it's the semicircle given by this. Right, this semicircle is in the xz plane. Alright, for us it doesn't matter how to, the drawing here is not as crucial as in the case of double integrals. So we need to parameterize this curve. So parameterize, now you know how to parameterize. This is again pre-calc. Parameterize this curve, and this is circles are parameterized by cos t sin t. So the curve r bar t will have y component 0 to begin with, because it's all in xz plane. I take x to be cos t, y t to be sin t, and my t runs between 0 to pi. Just make sure that at r bar 0 you are at 1, 0, 0, and r bar pi will be 0, r bar pi by 2, isn't it? I want cos to be, hold on, cos of pi, yeah, cos to be minus 1, that's right, and then sine is 0. So that's the parameterization. So this parameterization is correct. So r bar prime t is going to be minus sine t, 0 cos t. This is going to play the role of x and y, x and z. So now what is the integral f bar dot dr bar? This is going to be integral the components of f. Remember, let's write down f bar. F bar is going to be, the first component is minus z, second component is not there, that means 0, and the third component is x. So it's minus z comma 0 comma x. So it's minus z comma 0 comma x dotted with r bar dash, which is minus sine t, 0 cos t dt, and t will go between 0 to pi. So this is integral 0 to pi. Now you write what z is. Z is cos, z is, here is your parameterization. So z is sine t. So it's minus sine t 0, x is cos t, dotted with minus sine t 0 cos t dt. So it's going to be integral 0 to pi, minus sine is sine square t, 0 times 0 cos square. This is very nice and easy. So cos square plus sine square is 1. So the answer will be simply integral 0 to pi 1 dt, which is pi. Good. I think that should be good enough. It's a long lecture, but I wanted to do in fact more, but I think let's do the next bit in the next lecture.